You want to start in about 5 minutes?
No, let's gradually get started. Okay, good morning, everyone. This is a 2-day tutorial on MPI, and that thing is shining in my... Where can I stand? Okay. I guess I'm going to stand here by the lectern. The projector is very bright. For instance, if I look at Carlos, I just see a big bright blob of having been blinded by the projector. Okay, so the big problem is, of course, the remote connection. So remote people, please let us know if you have trouble seeing the slides and hearing my audio. There is a 30-second or so delay on the audio. 10 seconds, okay. It's not instantaneous, but anyway, so we should be good to go. My name is Victor Eickhout. I am in the HPC group at TAC, as is Carlos in the back of the room. So the two of us are the in-room experts to help you, especially the first hour. We'll have some getting started problems, undoubtedly. For instance, is everyone on the wireless? Okay, so we don't have people from outside who need a wireless pass. There are printouts of the lecture slides in the back there. So if you want to scribble notes, make sure to pick up a copy. People remotely go to the, I have listed the training site, training page in the portal. You can download the lecture slides there. They are under links and videos, not under files. And there's also a partly completed book that I'm working on MPI and OpenMP, which you can read. There's a lot of information in it. It's not optimally organized yet, but okay. This is going to be a 2-day tutorial on MPI programming. MPI is the main tool for programming on really large scale. At some point today or tomorrow around lunch, if you haven't seen our machines, plural, up close, we'll do a tour of the machine room, take 20 minutes or something. Anyway, so Stampede is 8,000 square feet of 100,000 cores, classical, and about 400,000 cores accelerator, coprocessor. So the only way you can use 100,000 cores is using MPI. Your laptop has a couple of cores, and if a single laptop or server is enough for you, then you can use OpenMP. But for really large scale, really MPI is the only game in town. Oh, let's see. How many people here are from some sort of physics or engineering discipline? Okay, that leaves you. How many people are non-engineering physics? Okay, so we have a traditional crowd in the room. Yeah. I wish biologists would start coming to this to these courses. They have a hard time using parallelism. There is a vocabulary gap between engineering and biology, etc. So they have the need, but we have a hard time transferring skills to them. Okay, MPI is programming on large scale. So the type of parallelism that you do in MPI is called SPMD, single program multiple data. So this means that you run on a couple hundred processors back there, and every processor is running an instance of the same program. It's not that there is one program running and somehow it manages to find all these processors. Every processor is running an instance of the same program. And somehow these programs know of each other's existence and they can communicate. Oh, very good. We have a biologist on the Hangout. Welcome. Okay, so MPI is now a good 20 years old. 1993 or 4 or so, and at the time, a PC computer was a gray box, and it had one processor in it that looked like one chip. The concept of core wasn't invented, and so you run one MPI process on your one processor per gray box. Okay, it doesn't look like a gray box anymore, but if you look at Stampede, you still see that there are nodes, so they kind of correspond to what used to be the gray boxes. These days, a computer is much more complicated. So if you pull out one node of Stampede, then you will actually see 2 chips in it. For the people that are going to take a machine room tour, we have a node that is open in the back, and you'll see that there are 2 chips in it. So, so what used to be one box, one processor, one process is now one box, is 2 chips, and every chip has, oh, this is an arbitrary picture with 6 cores per chip, but we're now up to 12 cores in Lone Star 5. And so what are you going to do with that? Are you running one MPI program per node or per chip or per core? Okay, so MPI basically pretends that this complicated world doesn't exist, and it still thinks that each MPI process is in a complete physical world by itself. So multi-chip nodes don't exist, multi-core chips don't exist. As far as MPI is concerned, this is what the world looks like. Every MPI program runs in its own world, and it doesn't see the rest. It needs network connections to talk to the rest. Let's see if I can. The screen setup is a bit. So you could actually acknowledge that the world is complicated, and you run one process per node, and then you run 12 or 24 or whatever threads. But for the next 2 days, the words core and thread don't exist. Okay, so we have a conceptual model that a core is a separate processor, and so all your MPI processes do not know about any form of sharing. Okay, MPI. So you have to. MPI is a library. You write your programs in C, and then you sprinkle library calls in it. So you write in C or you write in Fortran. Anyone here wanting to write in Python? Cool. Python has pretty decent MPI support. I think my slides incorporate that. Otherwise, look at the book. I tried to give the reference for every routine in C, Fortran, and Python. MPI is a library. So you write just regular C and Fortran, and you put library calls in there. Now, to compile this, you would have to add a whole bunch of compiler options. Here are the include files, these are the libraries, etc. So on any computer that has MPI installed will have a couple of things that look like a compiler, MPI CC. So you'd say MPI CC, your C MPI program. But this is not actually a separate compiler. It's just a shell script around your C compiler, and it just fills in the include paths and the link paths and the load library paths and the whatever, any further options that are necessary. So you will compile your program with these things, but they are just wrappers around your C, Fortran, C++, whatever compiler. Oh, Python, of course, is not compiled. Okay. And then you run your program with something that looks like MPI exec or MPI run. And on Stampede, you will use IB run. So there is some way of activating your program in parallel. So if okay, you've been given accounts on Stampede, but I actually do my MPI development on my local laptop, and so I call MPI exec -N12, and my laptop, it's Unix, it's a time-sharing operating system, so it just creates 12 MPI processes, and I can do my debugging. I get, of course, absolutely no performance, but you can do MPI on your laptop, and it will run just fine. If you'll be using Stampede, then you don't use MPI exec or MPI run, you use IB run. That'll be mentioned in a later slide.
General, what is the difference between MPI execute, MPI run? Is it just the same thing?
They're exactly the same. I think the standard says that it is desirable for an installation to have MPI exec. MPI run is, I think, mostly the same. And then you sometimes have MPI run _ something that can take advantage of architectural features. On Stampede, do use IB run. I think you can actually get an error if you use this. IB run is our optimized version that knows how to use the machinery of Stampede.
Is it the same in Star 5 as well? Or?
Yes, we try to make our clusters behave exactly the same, and so IB run works on all machines. Yep. Okay. Okay, let's get started. Just to make sure that we can run stuff. Connect to Stampede. Open 2 windows. Okay, these clusters, they work as follows. If you SSH to them, you wind up on your command prompt changes into login 1, 2, 3, 4, whatever, .stampede utexas edu. That's a login node. Login nodes are only for compiling and editing, not for anything more. There are on Stampede, literally 4 login nodes, I think. Anyway, a very finite number. That's why you do your editing and compiling. And then you somehow grab a compute node. We have 6,000 something compute nodes. So you grab one of those, and that's where you do your running. You do not do your running on the login node. Depending on how you do it, you will just plain get an error message. Or if you manage to do it, you will piss off our sysadmin and your account gets blocked, and it will take you 2 days to straighten that out, and that's 2 days lost productivity. Anyway, so you need a login window for doing the compiling editing, and you need another window for on a compute node. Okay, so we have I don't know, 5,000 users on Stampede, and we have 6,000 nodes, and the average user wants 10 nodes. Okay, that's a conflict. Okay, so so you may have to wait to get a compute node. Well, we're nice to you, so type idev -N2. So idev is an interactive session on a compute node. That is nice for doing development. Those sessions time out after 2 hours max, I think, 30 minutes. Anyway, that's an interactive session. That's nice for development, but in the end, if you start running production, you have to write batch scripts. We'll save you the effort today. So in your second window, type idev -N2. That means request 2 compute nodes, little n32. Okay, a node has 16 cores. So with 2 nodes, you get 32 cores. So this means you can now run 32 MPI processes. And minus T400 means don't expire for the next 4 hours. Right, if you create that, if you already have another project on Stampede, then it says, do you want to use this project or that project? And use the training one. It's called either training HPC or TGTRA, blah, blah, blah. Okay. Edit. Make 2 windows. Make sure that you can get an IDEV session. Raise a hand if you need assistance.
What was the name of the allocation we should use?
It's either training HPC or TGTRA something.
Okay.
If you have some difficulty accessing it, just let me know.
Yeah, because I have other allocations and it's
Yeah.
hard to default to those.
It should show up in your list of your logins.
Oh, this one right here. Okay.
That's the one.
Okay, cool. Thank you.
IDEV tries to be clever. It sometimes remembers your settings, so you can delete your .IDEV.rc. Then it,
Okay.
otherwise, it may by default try to use your other one. Yeah, okay, so this is slow down. Just completely remove You have another session open somewhere.
Yeah. Sure. Yeah, that's your option. Yeah. But either Nathaniel will have a key or Sergio will have a key, or Remy. Remy might have a key for that as well.
Project, you know, project I do register for the course.
It's fine.
Oh, Stampede and LS4. What do you do in LS4? Okay, let's assume that everyone has an IDEV session. We're actually going to do something. Exercise number 1. You don't know any MPI, so we're going to write a program that has no MPI in it. Just write a hello world program, compile it with MPI CC, and then use IB run to execute it. Write hello world and then do IB run hello world. I'll give you 7 minutes for that.
Chat looks good. Oh, you have the chat window as well for day 1.
Yeah.
Okay. It's not.
On the other hand, I should have. Okay. MPI exec or your local equivalent, I should have clarified that when you do that on Stampede, you do not have to specify how many processors you're using. By the way, -NP should work. Anyway, you do IB run your program name. That's all. Okay. The number of processors is determined by the IDEV command line. The IDEV says you get 32 processors. You run IB run your program 32.
Do you want to disable this projector?
No.
Sure.
Um,
We can do it through projectors.
Yeah, see, I don't like this screen sharing stuff. No, I'm fine.
We were doing
Where is my stupid mouse?
Is there a specific compiler we should be using?
MPI-CC
Yeah.
or
The specific
oh, in Intel or GCC, either way. Just use the default.
Okay, 'cause I'm getting like a license error or something.
Ah, you are trying to compile on the compute node. You need two windows, the login node and the IDEV session. You compile on the login node. The compilers are not installed on all the compute nodes. Sometimes they are, and sometimes not.
Okay.
It depends on the time of day and the season. And okay, has everyone run their Hello World program? Anyone stuck on anything? Okay, so ignoring a couple of strange error messages, if you IB run that program, you get 32 times hello world. Okay, so this is because of the SPMD model. You ask for 32 processors, and let's ignore the node idea. The little n, 32, you ask for 32 independent processors, and so you get 32 processes. Each of 32 processes is a copy of the same executable running. And so, so you have 32 programs running, and each of them do hello world. Okay? So you get 32 messages hello world to your screen. The point of this is that I really want you to see the SPMD model. Your program from statement 1 is running so many way parallel. It's not like the program does some sequential stuff and then magically it becomes parallel. There is really, if you're a regular user, up to 4,096 programs, each saying hello world, okay? So this is the SPMD model. You have independent processes running all the time. Okay, next we're going to turn this into a real MPI program. So I'll make a copy of it. We're going to turn it into an MPI program. So you need a couple things to make it legal. So MPI is a library. So you're going to be putting library calls in your code. And so it needs to know what the prototypes are. So for C and C++, do include MPI.h in your program, somewhere at the top. For Fortran, use MPI-f.h. Yep. And then in your code, you need 2 lines, MPI init and MPI finalize. If you're not going to be using command line arguments, you can replace argc, argv with just zeros. So for C programmers, MPI init, 0, 0, and MPI finalize. Okay, MPI people, sorry, C++ people can now get started. Python, it goes like this. So you, on Stampede, module load Python MPI, and then include that statement from MPI for Py import MPI, and there is no initialization statement. Okay, here's exercise number 2. Make a copy of your Hello World program and put MPI init, MPI finalize calls in it. And just for the heck of it, put 1 before MPI init, 1 between init finalize, and 1 after finalize. So hello world 1, 2, 3. Okay, anyone here speaking Fortran as their main language? Okay. I thought I'd listed the syntax. Fortran routines are largely identical to C routines. There's one exception. There's one big exception. Every Fortran routine has a final parameter that says error code. So MPI finalize in C has 0 parameters. In Fortran, it has 1, an integer error code. If you forget that error code, the compiler doesn't catch it, and you get very colorful error messages during runtime. This is a complete headache. I have no idea why they don't turn MPI into a nice Fortran 90 interface with interface blocks. Anyway, but there it is, Fortran. Add error code to every routine as a last parameter. Very important. And now there are a couple of routines that are different between C and Fortran. For instance, Fortran does not have a standard mechanism for handling command line arguments. So in Fortran, MPI init has, I think, no arguments. So is that correct? Not even a zero. Just the error, right? Yeah. I thought I'd given the syntax here. I should really do that. Anyway, so in Fortran, MPI init, just error. Okay, with that, do exercise 2. Make a program with MPI init and finalize calls and print statements before, in the middle, and after it.
track down Dean, so we're gonna get.
Right, I just saw him. Does anyone here have the sign-in sheet on their desk? It seems to have gone missing.
Oh, it's right here.
You got it? Okay. Okay, another remark for Fortran users, your file name extension has to be capital F or capital F90. Otherwise, the preprocessor line is not recognized. Sorry, I mean. Okay.
Just a question on the Python.
Yes.
So is this done outside of the script?
Yes, that's shell.
So I'm getting this on both the login and I mean, I'm only mainly doing C, so if we can't get Python, it's not a big deal. I work in Python as well, so it'd be interesting.
Do you have one of these in your office that I can bring for you? Online and just a webcast, right?
Yeah. Yeah. Apparently, sharing does take battery power.
Yeah, it does.
Yeah.
All right, I'll go grab one.
Okay. Yeah, you can take from my office or anywhere else you can find one. All right. So what was happening there? Carlos, is it still necessary to load a Python MPI module?
No, I think you just load a regular Python module.
Okay.
That has MPI for Py as one of the other.
Okay, so my information is outdated.
I think Cloud updated that.
Ah, I see. Okay, there's your answer. Just load module load Python. How's everyone doing on this exercise? No one stuck? So, okay, so you should see a whole bunch of hello world before, in between, after. This is the program that I wrote. Hello world before, between, and after. And if you run that, you get a whole bunch of statements. Anyway, this is to emphasize that the init and finalize calls are not someplace where your program magically becomes parallel. Your program runs parallel from beginning to end. Okay, SPMD, single program, multiple data. The multiple data is the fact that they're all in their own little world with their own processor, their own memory. Okay, so I'll assume that everyone has this working. Okay, here's a fun one. Okay, so you need to look at the downloadable book for the syntax, or look up the syntax online. Oh, it's actually here. Okay. So far you've been running your MPI programs, and they were all completely identical. So you asked for 32 processors, you get 32 identically running programs. Okay, how do you do something useful if they all do the same? Okay, so your processes can actually figure out that they are different from the others. So the first way that you can find out how one of your processes is different from the others is asking for the physical processor name of where they're running. So so make your next exercise and use the command MPI get processor name. That works as follows. You give it a character buffer and you specify how long the buffer is, and then it tells you, and it puts the information in there, and it tells you how many characters it was. If you're used to C++ and standard : string, and this is extremely primitive, but there is a reason for it. in addition to the fact that MPI is 22 years old. Okay, so use that routine. In Python, it's pretty easy. Use that routine, write a program, and run it, and confirm that you are indeed running on 2 different nodes, so 2 different actual processor names. Anyway, type. I'll get some. It's okay. Get processor name. What am I doing wrong? Huh. Yes. Right. The library. No, that's a prototype.
Okay, gotcha.
Yeah. This confuses students all over. Okay, one word of clarification. So in the book and in the slides, if I show these little bits of C, Fortran, Python, that is not actually a legal code segment. In Fortran, it's almost. You need to put a call in front of it. This is the prototype. So this is the description what the routine looks like. So in C, you don't type character star name. You type name, where name has been defined as a character star. Okay, so this is copied from the .h file. This is not copied from an actual source. Okay, these are the prototypes. In Python, I actually kind of fudged that because Python prototypes are kind of hard to understand something. Anyway, so for Fortran programmers, put a call in front of it. For C programmers, don't write character star name, write name where name has been defined a couple lines earlier as a character star. If you want to cheat, this is what I had. Yeah. How's everyone doing with this one? Anyone completely stuck? Anyone saying, I'm bored, get on with it? So the output of my program says I am running on C403.203.stampede.edu, and it says that 16 times, and then it says 16 times that I'm running on C403.204, so 203 and 204. What on earth does that mean? Well, C means it's a compute node, 4 means it's Stampede, and that 03 is cabinet 03 in the machine room. When we take a tour, I'll show you the labels so you can actually find the physical node that you're running on today. And then 203 is is it 1 and 2 for top and bottom half, and then 04 is the numbering? No, there are 20 numbers. Anyway, it's a coordinate in the machine room. I forgot the precise translation, but the 4 indicates what cluster you're on, and then for the rest, it's a numbering of cabinets, top half, bottom half, and the node inside it. Anyway, so you see here that a node has 16. Okay, I wasn't going to use the word cores, so let's call them 16 processors. A node is 16 processors, so since you have 2 nodes, you get 32, and so your first 16 run on processor C403.203, and the next 16 run on 403.204, or whatever it is in your case. But make sure you get 2 different names.
You had a question? Just before the closing. No, one line. 5 spaces to the right. 5 to the right. 2 to the left. One more. Now insert space %s. Oh, and backslash n. Oh. That's it. I just write the formula.
Is that just to put name?
Okay, printf says print the following string and %s means that you're giving a second argument that is a string. So and then backslash
Or is this name the same thing as
no, it's a print, so it's a print string to the screen. Compile this. Source.
Is that because I
Oh, that's the problem, yes. Yeah. Like, yeah. Oh, there you go. If you're more comfortable in Fortran, you can do the whole thing in Fortran. Just every MPI routine is a call MPI routine, and make sure to put the arrow parameter at the end. Failed exec. Specify the wrong name or something.
So I'm trying to run Python script and using run.
If you are happy run.
Yeah, and just getting a bunch of errors. I think it might have something to do with I have to load the specific Python.
I should just call to the easiest process name.
Yeah.
Well, it's yeah, it should run. It should still MPI Workshop do process name.
Yeah.
Space. Yes.
Okay.
I think that's okay. As soon as you say import from that library, because some people actually
Okay. Yeah. Okay. Sweet. So when you're like, I was using something like, just like a, okay, so if I was using that, do I have to download a specific version of Python? Yeah, so I can download the module, but I was just wondering if you were prefacing this one with Python edition.
Everyone doing okay with this exercise?
Okay. Good to know. Yeah.
I mean, if you switch to internet,
Right, right. Well, thank you for sharing that knowledge.
Okay, so with this exercise, you've established that your programs are not all running on the same node, that they are running physically on different places on the machine. Now, knowing that physical location is actually not terribly useful. In most cases, what you actually use is the following. Where did my mouse go to? Oh, here. So if you start 32 processes, then the most common MPI calls are to ask the rank and the size. So size says, reports to you how many processes are there. So you start 32 and MPI com size will report 32 to you. And com rank will tell you have 32 processes, and each of these has a unique rank, which is 0 through 31. So you call MPI com rank on your process, and it will tell you 17 or it will tell you 22, depending on who you are. Okay, so what is that com? Well, we'll get into that sometime tomorrow. MPI has something called communicators. A communicator is a group of processes. And for now, we'll just use the default group, which is typed out MPI com world, which means everything you've requested. Tomorrow, you'll learn how to make subgroups of that. So there are these two routines that tell you how many processes are there and what is my number in that club. Exercise. Write a program where each process prints out what its number is and it prints out what the total number of processes are. So I would say take your Hello World program and try to spit out hello from processor 12 out of 32. Okay, so use the com rank and com size calls in your program to print out a message. Hello, I am number 5 out of so many. Yep. That's it. Just checking.
Yeah, yeah.
Run a different program.
So we should be okay, right? I can ask for an additional 5.
2,800, that's, how many people do we have?
11 here and 15 people as
2,800, that's divided by 16. I shouldn't be talking about that.
Everybody's on the line
It's
session before.
Almost 200 node hours. Divided by 50 people is only 4 hours per person. I would top it off.
Supplement.
They have their files here.
Yeah.
Which? Charlie's giving an exam today.
How's everyone doing with this exercise? Okay, thank you. Anyone in trouble? Okay, I see no overwhelming protests. Hey, Carlos, is there a difference between character star and name and character name parentheses? I just wrote here. I just wrote the same thing, and it seems to work fine. But I've used character star as opposed to character name as an array.
Oh. I've never used
Yeah, I'm not all that comfortable with Fortran either. Yeah. Okay. Yes. Oh, okay. I'll help you for a minute, and then I'll go on.
Oh, is this returning? Yes. So it returns an integer, so that's just an error. This is the actual result. So I initialize this, and I pass the argument as yes, and this then writes it. It writes it to this variable. Yes. Yeah. That's
Okay, that's another point that I can clear up. So in this prototype, it says int MPI com rank. So the function returns an int. That is not the int you're interested in. That is an error code, and it's practically useless. So in fact, I just completely discard it. I treat it as if it's a void MPI com rank. Then the communicator. And so int star rank means that you have an integer parameter rank which you pass in. Which one was this? This is exercise 4. This is how you use it. You create an integer parameter, you pass it in with an ampersand because it says star rank. So it's a pointer to int. So you pass it in with an ampersand, and then you print out I am whatever. MPI CC minus O exercise 4.c. What did I do wrong? Okay, so everyone is reporting a unique rank. Oh, and here's an important thing. Screen output from MPI is pretty much guaranteed to be a mess. It is completely impossible to synchronize your processes. There is no way, barriers, whatever, screen output. Okay, so you have to imagine there's a node here and a node there, and they're running your program, and then here is your login node. And so the I/O gets buffered here, gets buffered there, gets sent through the network, gets buffered on your login node, and then at some point it appears on your screen. This is guaranteed to be a mess. There is no way to get clean screen output if you really, unless you print everything from process 0 or something. So don't try to pretty up your screen output and just live with the fact that it's going to be a complete mess. Okay. So did everyone get that more or less working? So I quickly edited my own file. So integer my rank. You do MPI com rank. Has to be after the init, and then you print it and you finalize. The print can actually go after the finalize. It's just a parameter, so it lives forever. So MPI init is just setting up the internal bookkeeping of the library. It doesn't do anything magic with parallelism. So before the init statement, a process basically doesn't know what its rank is because the library hasn't been set up. Carlos, can you take a look at the gentleman on your right?
I had a question about
Oh,
MPI and
sure.
So, like in this last exercise, we used MPI combo. Is it that variable, right? We did not have access to that without or before the init statement, for example. I'm just trying to figure out the init and finalizer.
Init, basically anything you do in MPI has to go between init and finalize. There are a couple of exceptions.
Because we have that like the print like exercise 2 or something where it's before and after. Also
Right. So before init, you can do any regular C code. After finalize, you can do any regular C code. So okay. Let me make that point. So, oops, not this one. So I ask what rank am I, which you can only do between init and finalize. But after that, the rank is just a regular C parameter. Everyone has their own copy of this C parameter. And so I can still print it afterwards. See? So there's nothing really magic about MPI init and finalize. It's just that anything you do with init and finalize has to go in between. Okay, there is a test where you can test if you are already initialized, and obviously that can be done before. And there is a test that asks, have I already finalized? And you can do that afterwards, but that's a minor point. Okay. Okay, so I hope that sort of clears it up. All right. So you have your program for exercise 4. Make a variant and make an exercise 5 where only process 0 says there are so many processors total. Okay, so right now everyone had a completely identical program. Everyone asks, I am number so and so, and then it prints I am number so and so. Okay, now how would you approach a program where only number 0 prints out there are this many total? Okay, how are you going to do this?
Use an if statement.
If statement, correct. So all your MPI processes do exactly the same thing. So if you want that only one of your processors opens a file and not all 4096 of them, then you need an if statement. So an if statement is one way in which the processes can distinguish themselves from each other, where you can get different behavior on one than on another. Okay, do exercise 5.
I'm saying I'm processing. I actually did that. Well, no, I can remember, but I don't want to say I'm 0 out of 32 to 31. That's a great difference. So I can just,
Yeah, I didn't know derived existed, but that's because Python basically trusts you. So you can get at internals, but I wouldn't do it. I would use the functional interface. Yeah. That's nice. Okay, so. Oh, yeah. This it is.
So we said that this was something now.
Oh, it's only 20. Okay, I'll assume that everyone is watching cat videos by now. This concept of having identical processes that somehow do something not quite identical, that is called functional parallelism. So function meaning doing something. You have a bunch of processes and they all do something slightly different. For instance, if you are doing a search, let's say traveling salesman problem, then you could give every MPI process a different route to explore. So your search space has to be parameterized somehow, but then every processor knows what its rank is. And so if in the traveling salesman problem there are 10,000 different possibilities to explore and you have 1,000 processors, then every process figures out, I'm going to try these 10. Okay? So that's functional parallelism. And we continue with exercise number 6. It's kind of subtle. There is functional parallelism and there's data parallelism. So functional parallelism is every processor has a different activity. Data parallelism is they sort of have the same activity, but they do it on different data. Yeah, well, it's kind of subtle, but anyway, so far you have not allocated any data that you're operating on. So we're strictly exploring how can you do different things if you know which process you are. Okay, so exercise number 6, functional parallelism. You have a search space. Is the number 2 billion and a couple a prime number? So any, of course, any factor of this number is at most the square root of this, which is around 45,200. Write a program that tests if this number is prime and do it in such a way that every process tries a different part of the search space. And for now, if you find a factor, just print it to the screen. So no summary statement or anything, just print any factor. Okay, hit it, exercise 6. Mm-hmm. Right, so for the people that are doing Python, I just put on the screen how I write this stuff in Python. So because you're using com_world so often, I just make a variable com is MPI com_world, and then many of your routines are in the com object.
Okay. Suppose you have the numbers 1 through 20, you have 2 processors. Yes. Okay, so if you have 20 numbers in 2 processors, probably 1 through 10, right? But be careful about saying you have to tell them. It's a bunch of independent processes, so they all figure out for themselves, I am going to do this much. There is no central authority that tells you are doing this, you are doing that. There's nothing central. Okay. Two processes. 0 and 1. So, how do I figure out what I do in numbers? How do I come to the conclusion that I use 10 numbers? Okay, yeah, on rank, size. Okay, so size, you say, is the number of tokens of any subject. And then the size, you can start point. Size tells you there are 20, 32, 56 processors. Okay. So you have 4,000 or 5,000 numbers. You have 32 processors. So they all take 4,000 numbers. So now you need to figure out which. So then you use the rank to give everyone different start points.
We always need that.
So I can do this fine if I try to print out this factor. Both important exception.
Yeah, I was getting that too.
I can run that loop, but once I try to actually print. Yeah, if I can't good state now, it doesn't give me
So I can find exception.
Yeah, so if I do this.
Well,
It's whatever the students first. Wow, so, I mean, it could be
just
that
I. This is a C program, right?
Oh, see what.
Are you combining with C++? Okay. Remove I/O minus and S3. String of page should be standard by error.
I see. So this way, define
Oh,
well, no, what I'm saying is, instead of having these instead of the statement, calculate then if x equals 0. That way you can print.
Yeah. If you remove the print statement, maybe the compiler says, okay, this conditional.
Well,
And
this is
so-
gonna skip the whole loop.
Right.
This is not in binary.
GDB.
each process to check. First check first. The way I'm checking is not interested.
So,
1, 0.
so mine is mine. Give mine a better name because you're confusing yourself.
So what is the process? Process.
So,
So was for processor 1. To check. First. Basically, I'm gonna take number.
Oh, yeah.
One.
each process needs to check this many.
Correct.
So, so that's how many you need to check. It's not typing the screen. So this is how many you need to check. Okay, now process 0 checks which okay, this many is going to check. So which process is going to check?
I'm gonna check 1, 2.
Okay, very good. Okay, so 0 0 gets a certain range, 1 gets a certain range, 2 gets a certain range. Okay, how do you determine the starting endpoint of the range? So for the derived, so 0 gets plus range. Plus 1 gets. So I could leave this.
I created an array, it's just this one.
And then I don't know if it's necessary. So you test this range. So it's
Yeah.
okay. No worries. Okay, so this is the rank round. Now how do you find it? So your process is 17, so you compute which range. What's your range? Okay, so in general, our range is okay, there you go. So that's now you write the loop statement. Now you write the loop statement.
That's what I'm doing.
I need to.
Those two numbers there, right now, it's the average.
You know what your process number is, you know what the total number is, so you can find out how many numbers you need to do. You know what your number is, so you know where to start. Yeah, why would you do for other processes? I'm using those. Throw away that code. That code is essentially wrong.
Well, okay, but what are your most? It's gonna be
Yeah.
1 over, like 1 over.
Yeah.
So, yeah. If that's no problem, then I guess.
My rank is to get points. My rank is 1 over never. I have no idea what this is. This one is correct. All right. More or less.
Oh, that's a good.
Syntax errors, but conceptually you're there.
Using it.
Just them.
Yeah.
Okay.
Just like that, verify first, now do that. Okay, so. Okay.
You can actually see the name download.
Sure we didn't do something really dumb.
So where is,
It's printing it outside the text. Over inside.
there's
It's where we
somebody at home right now, it seems to be-
also try to use like localized language. Just like
Years, well, years.
I mean, I checked it, and I checked it with them.
Three. Okay, that's me. Yeah.
Okay. So, someone says never use vowels, I, but it was vowels. So,
Yeah, so I have that here.
so, okay. Yes. Okay. So yeah, here, my rank is high. Okay, now suppose that in this next code, my rank is high, so every word is high. Oh, okay. Okay. Move, start still. That doesn't change. Now it says, if my rank is high, it's higher. Oh, and then you curve.
You're just trying to say how much.
Because in unit 4, you only execute it for my rank. Do you agree with that? So basically, you are losing access. You run through See, this code goes for every process. So why does every process look at what every other process does? You are number 17, so you only need to do the work for 17. You don't have to compute 12 does this, but I am not 12, so I'm not doing it. 13 does this, but I'm not 13, so I'm not doing it. So neither, but yeah.
Yeah.
So, anyway, you can never be the loop as well on the outside. Actually, I might get out of
On the outside of the text, we're going to do
Oh. This is chat just something with a module. I mean, because when I run the portion,
Can we use really the modules? You were trying to say.
Oh, did you find it?
No, something with this. So we can print out like then once I even do this, and actually compute the module.
Oh, minus. Oh, use a dash code afterwards. Oh, okay. These guys. Oh, yeah, I was looking for this one. So,
Same thing.
yeah. So,
have something doing this module.
So let's see, compiler doing some optimization. Each process needs to show sorting numbers. Okay. So that they didn't know total number.
I've been having the same issue with them.
You're basically finding all.
I was just making sure that it's not something to do with that.
There is no optimization, but each process, so there's 32 processes. So each process should be 30.
Alright, so. Start on lines, you find it.
Yeah, I've got the C version.
How are we splitting?
Okay.
So what you do is define as well. So this loop moves over
Sure.
each one needs to check 14 and 31. It scales this by 30%.
So where is
Range
range?
equals 1. Range is obviously
Yeah, but how are you,
Go on.
how are you where this is the logic process?
Yeah.
So I go, I just say,
Oh, that's just because I wasn't printing it out. So I was having issues with this.
I just go range.
Advisor, I was getting like a weird floating point error.
Right.
And so like,
Everybody's running different. So we need some way to be able to tell. I'm running zeros. I run this section.
oh, I don't get the. No, I
Now,
was.
well, everybody's all.
Yeah, but there was another reason why it was, oh, I was getting the floating point error because I was testing, I was using, basically, so I was starting my floating point at 0. And so it kept trying to do the define, it kept trying to find the major, and it was, so it got rid of that.
Some number.
But then.
So you
I would say,
iterate as you are right now, from say range 0 to range 31. And then clear inside this, so you say, if my range is equal to here,
I will try.
my range is equal to 5. You set my lower line. So it only operates on that section. So this makes the logic correct.
So can I just put an if statement outside of this for loop that defines
Okay, we're back in business. I think I've looked over everyone's shoulder and everyone has something working. Yeah. Oops. Okay. So you have your rank and you have your size. And one possible solution is that you find local number which is divided by the okay, so int and global is the square root of n. This program is not going to compile because I'm not defining everything properly. The local number is then the global number defined divided by the number of processors. And then you do my local is my rank times n local and, sorry, not my local, my low and my high is my rank plus 1 times n local minus 1. Something like this, and then you loop for int candidate is my low candidate less than my high. Okay, if I do less than, get rid of this. And you do your test here. Okay, that's this is one possible solution. Solution 2, which no one today has found, is this one. Int candidate is my rank, candidate less than whatever, less than n global, candidate plus n is processor size. Does everyone see how this works? So instead of giving every processor a disjoint contiguous block, you let every processor try a strided range and you just give them different starting points. Okay, you can optimize this and filter out the even numbers. So there are two basic ideas. One is block and the other one is strided. Both of them work. And then there is a non-solution that goes as follows. For me is 0, me less than the number of processors. If me is my rank, then I compute my low is whatever, and I do a for loop. Okay, so this is not a good solution. Although it is syntactically correct, it is semantically correct, and it runs with the right performance, but this shows a misunderstanding. This is SPMD. You write one source, but it runs 32 times or 256 times independently. So you know which number you are. And so you only have to look at the work that you're going to be doing. So if I'm processor 16, I don't have to see, okay, processor 1 is going to do this, but I am not 1, so I'm not doing it. 2 is going to do this, but I am not 2, so I'm not doing it. 16 is doing this, and I'm 16, so I'm doing it. Okay, just skip that whole loop and just say, I am 16, I am doing the following. Okay? This is a strange idiom. Statistically speaking, I don't know, 1 in every 20 students or something will chance on it. And so writing this comes from a mental model of computation where the fact that there is one source, you think that there is one running program, and then magically somehow it becomes parallel. No, it's not. So you really need to have the SPMD model in your mind. So you never have to look at other programs are doing this, but I am not them, so I'm not doing it. You can just look at your own. Rarely will your code actually loop over other processors. Probably not in this 2-day course. Okay. There is one reason I like the Apple Terminal program, is that it saves a complete session log. So at the end of the day, I will save this as a text file and attach it to the course. So you see everything that I've done in all its ugliness with arrows and all. Okay. Where are we? That's exercise number 6. Okay, so up till now, we've been warming up to the notion of SPMD, of how MPI programs run. And I hope you now all have sort of the mindset of identical running processes that can somehow figure out why they are different from the rest, and they act based on it. MPI type programs are sometimes called symmetric because every process is basically the same. And in scientific computing, you will often do things that are symmetric, where every process is sort of doing the same activity, but on slightly different data, hence the SPMD, single program, multiple data model. Okay, so we're going to explore this fact that everyone is kind of the same and look at collectives. Let's see if I can make this slightly. So a collective operation is something that happens in parallel, where you're combining data from all processors. Either you're combining or you're giving out data. So it can go two ways. Every process has data and you want to bring it together. For instance, you want to, in the prime number example, everyone has the information, I found a factor, and now you want to bring that together in a global fact, yes, this is a prime number. Or one process has data and you want to spread that around. So once you've found the smallest factor of your prime number, maybe everyone wants to know that factor, so you would have to somehow communicate that fact to everyone. Okay, so those first two bullets have a root process, namely the one that brings everything together, or the one that spreads out the information. And it still doesn't quite fit on one screen. I hope it's still readable. So there are 4 basic cases. There is data gathering. So in the prime number case, everyone has found a factor, or otherwise says 0 if it didn't find one. And now process 0 wants to collect all that information, and it collects the factors that everyone has found. So that's gathering. You bring together all the information. If you collect all the data, but you want only some global summary, like this is prime or this is not prime, then it's called a reduction. So you bring the data together, but instead of keeping all the items, all the factors, you summarize it to something, and that is called a reduction. And then the inverses of gather and reduction are, instead of bringing everything together, you have one number and you send it to everyone. That's called a broadcast. On the other hand, if you have individual data for everyone, so process 0 has gathered together that these are all the factors, and now it wants to communicate that to every other processor. Nope, that's not a good example. We'll come up with examples later. Suppose process 0 has read a text file and it found information, and now it's going to say, process 1, you're going to work on this, 2, work on that, 3, work on that. That's called scatter. So you send individualized information. Here's a picture. Broadcast, send the same data to everyone. Scatter, the root has an array of items and sends one item to everyone else. A reduction, everyone has a number, you bring them together and you summarize them. You do a sum, a product, a max, a min, a logical XOR, whatever. And then finally, gather is everyone has some amount of information, you bring them together and you put them in an array, so the root preserves that stuff. Okay, here's a mental exercise. How would you realize the following scenarios with MPI collectives? Okay, so here you have your 4 collectives: broadcasts, broadcast, reduction, scatter, gather. How do you do the following? Each process has computed a random number, and you want to print only the maximum of these numbers to your screen. So everyone has a different random number, and you want just the maximum printed to your screen. Oops. How would you do that with these 4? Okay, I've heard 2 suggestions, gather and reduction. It's a reduction, right? You only need to know the maximum. So someone does a reduction with a max operator. And then, so that's the root process that's doing the combining. And then the root process can print it out to the screen. Correct, reduction.
Root process gathering data from all individual processes.
That is also possible.
I mean, is there a simple way in what reduction is?
We kind of have to go into internals here. Okay, so if you do a reduction, then 2 processes do not have to send it immediately to the root. They can send it to someone else, and that intermediate processor then does the maximum. And here are 2. So imagine a tree. Every pair of numbers gets combined, and it does a maximum. And then every pair of those combinations gets combined and does the maximum. So it's an efficiency argument. If you do it, this is kind of jumping ahead to a slide that's coming up pretty shortly. If everyone would send to the root and then the root does the maximizing, then the root has to receive, in this case, 31 messages. If you do it with a tree, the root only receives 2 messages. So maybe it's faster. Okay, we'll go into that in some amount of. We'll go into that slightly later. Anyway, but reduction is more efficient than gathering. Okay, so to compute a maximum of a bunch of random numbers, you would do a reduction. Now, again, everyone has a random number. But now you want everyone to scale their random number by the maximum value. So you need to have the maximum, but then everyone wants to scale by it. How would you do that with the following scenarios? Yeah, you would do a reduction so that the root knows what the maximum is, and then the root does a broadcast so that everyone knows what the maximum is, and then everyone does the division. Correct? Okay, every process has a random number. In bullet 1, you only looked at what is the maximum. But now in bullet 3, you want to know who has the maximum. So how would you do that? You've already spoken. I think you had it correct. So who in the rest of the room wants to? So the question is, you want to know who has the maximum. No? Okay, so instead, if you do a reduction, you lose the information who has the maximum, you only find the actual maximum. If you do a gather operation, then you wind up with an array that has in location 0 the value of 0, in location 1 the value of 1, 2 the value of 2. So the root can then go through the array and note who has what is the maximum and at what location was it. And so that location corresponds to a processor. And so the root knows the maximum was at processor 5. And yep, there is someone in the chat window who has it correct. No, wait a minute.
You can also do that by the reduction where you carry out, you have one more variable.
Yes. If you do a reduction on a real integer pair, the random number and the location, but that is not built into MPI, so you have to make your own reduction operator. You're absolutely right, but that's...
Okay, but if I just wanted to just compute the maximum, then I already have direct those that those of me ever want to make do a pairwise comparison.
You never... The pairwise comparison is something that happens under the hood.
Oh, okay.
The only thing you know is these 4 operations. Semantically, how they're actually implemented, you don't particularly care. Maybe by this is the semantics, and whether that's realized electronically, hydraulically, or through voodoo doesn't particularly matter. We're here mostly concerned with semantics, and we'll barely touch on performance issues or implementation issues. Okay, right, so depending on what sort of scenario you have, you use different MPI collectives. Okay, we will explore a couple of collectives, but there is a whole bunch more. So the root process is the one doing the collecting or the disseminating. Instead of a root, you have collectives that do an all something. So if everyone wants to have the result of a reduction, then instead of specifying a root, you would do MPI all reduce. If you do a scatter, sending individualized data, but the amounts are also individual, then there is a routine with a complete headache of a calling sequence called scatter V. Sometimes everyone needs to send to everyone. That's called an all-to-all. Sometimes you're doing a reduction, but processor 5 doesn't want to know the maximum of everyone. It wants to know the maximum of 0 through 4. And process 12 wants to know the maximum of 0 through 11. That's called a scan. They're pretty rare. I'm just mentioning that they exist, and they will not happen in this course. Okay. So what does a typical MPI routine look like? MPI bcast, and Fortran is completely the same with an error parameter at the end. You have a buffer, a count, and a data type, and you will see that everywhere. Buffer, count, data type. So the buffer bcast is a broadcast. So the buffer is the data that's being sent. Count is how long is your buffer, and data type is what's in the buffer. And then root is who's doing the broadcasting, and MPI com. You will, for purposes of this course, always use MPI com world. Okay, so the buffer. Everyone has to create the buffer traditionally with malloc or just declaring it as an array. If it's a scalar, you can just pass a scalar. The root puts values in the buffer, and then everyone else leaves the buffer undefined. And did that work with moving the declaration outside of a loop? Dang. Okay, when I've said everyone else leaves the buffer undefined, in Fortran, sometimes the compiler thinks this thing is not being used, but it is in MPI. So the Fortran compiler can sometimes trip up on. Anyway, the data type is something like MPI float, MPI int. Look in the book for the table, or just look it up online. MPI float and MPI int are the C terms. Yes, in Fortran it's MPI real and MPI integer. So slight difference between C and Fortran. Com is usually MPI com world. Okay, one more word about the buffers. So in C, it's defined as a void star. Okay, your buffer is actually, it's always an array. So it has to be an int star or a double star or a character star, whatever. But to be able to send anything, it's defined as a void star. Okay, in C, if you want to send an integer is, or a scalar, sorry, that's what I meant to say. If you want to send a scalar, it's an int or a float or a double, but it needs to be an address. So you would write ampersand of x, or if you want to be really clean, void star of ampersand x. If x is an array, then you just specify x as the address, or you write void star x. In Fortran, this is simpler. Since Fortran always passes by reference, both scalars and arrays just put the name there as the buffer. All right, for the couple of people that are doing this in Python, there are two versions of every routine. There is MPI reduce and there is MPI reduce. And I can never remember which of the two is which. So the lowercase one can send native Python objects. This is beautiful. This is fantastic. I wish I could do it in C. Actually, I could do it with the Boost library. But you pay for this functionality. If you know what pickle is in Python, what Python actually does is it takes an object and it converts it to a self-documenting byte stream, and then that is being sent. So it's extremely general, it's beautiful, it looks like real Python, and it's also very slow. I've done some testing, and if you send, I don't know, a couple of kilobytes worth, then it's 10 times slower, and if you send a megabyte, it's 100 times slower. So only use this if you really want to send a Python object. The other Python variant uses NumPy, so you also need to do not module load, what? Import, thank you. You have to do import NumPy, and then you create a NumPy object. Sometimes this is pretty counterintuitive, so there's a bunch of examples in the book where I show how this is done. Okay, no, I don't think I like this exercise. Do I? It's oh, this only works in C. Next one. Okay, let's do exercise 9, for which you need to do. Yeah, I kind of want to get on with it. So exercise 8 is if your program has command line arguments, I never trust that everyone gets the same command line. So I let process 0 look at the command line and then broadcast the information to everyone else. Command line options are a really nifty way of making your program customizable. So maybe you can do this at home. It's kind of cute to figure out how it works. In Python, you would import the module sys, and then you have sysargv. So Python actually looks pretty much like C in this respect. Fortran, I don't know if command line arguments are standardized. You happen to know that, John? I thought they were.
It's not good at command line argument.
Yeah, I thought they were adding it.
It's standardized now, but it's not.
That's what I.
It's not easy to use.
Okay.
You have to call
Yeah.
a built-in function.
Yeah, I think they added it in 2008 or something, but I've never used it. Okay, so we'll skip that exercise. Okay, so we just looked at MPI bcast, which has a buffer account and a data type. So you give it a scalar or an array. You say this is one MPI integer, or this is an array that contains 5 MPI doubles. Okay, now if you do a reduction operation, then it looks slightly different. There is a send buffer, so everyone puts their data in it, the data that needs to be sent to the root. But there is also a receive buffer. MPI plays it safe. MPI is not going to, so the root puts information in its send buffer, and MPI does not want to override it. Because that buffer belongs to you, and maybe you want to keep that information. So a reduction actually has a receive buffer, which is only meaningful on the root, and that's where the reduced information winds up. So it's buffer and another buffer, and then count data type. MPI op is MPI sum, MPI max, whole bunch of things. Some of them are the same between C and Fortran. C has no Boolean operation. Fortran does not have bitwise logicals, so there are a couple of differences. The table is in the book. Anyway, with reduction, do exercise 9. Write a program. Everyone computes a random number. If you don't know how the random number works, here are 2 code snippets that work for me. It's not necessarily the best way to do it, but that's what I'm using. So everyone computes a random number, different random number. Right, so how do you force your processes to generate different random numbers? Well, your random number has a seed, and so you need to initialize the seed with something that depends on the number of processors. So you seed the random number generator individually. You can do it this way, or you can use the time function to the time of day function to initialize it. There's a bunch of solutions for it. Process 0 then prints and finds and prints the maximum random number. And just to make sure that you're doing it right, let everyone print its value, just as a safety check. And after that, when you find the maximum value, everyone scales their local value by this maximum. So you need to do a broadcast. Okay, so this is just to have you write this and make every mistake that every beginner makes. So go write exercise number 9. We are at 20 minutes till noon, so I'll give you until noon. By noon, we break for lunch, and then let's take 50 minutes for lunch. So come back here 10 minutes till, and we can do a tour of the machine room if you want, and otherwise we'll start again a couple minutes after 1. In case I said 2, should be 1. Don't remember what I said. I'm a late luncher. Yes?
So this is kind of a general question, these buffers. How did when the root is receiving buffers, like it's receiving the sent, how does it not overwrite itself? Like,
that's because it has 2 different buffers. It has a send buffer with its own local data, and it has a receive buffer that contains the reduced data.
Right, but if you're receiving all sorts of different, if you're receiving many receive buffers,
yeah,
and then you want to, are they just like separate receive buffers? Are they not writing at the same spot? Or is it the fact that these
okay.
buffers exist Is that the point, that these buffers are their own thing? And they're not
You could, for instance, imagine that under the hood, the MPI says to the network card, I'm expecting data, put it in this buffer, and then it says to the network card, I'm expecting another message, and when it comes in, it does the max of these two, and then it says to the network card, I'm expecting another message, and when it comes in, take the max. So MPI uses internally some amount of buffer space. But
Actually, this is a fair amount of buffer space. This is where the runtime has queues of messages that are going to be received, and it can manage multiple messages coming at the same time.
yeah, but if you're going to be expecting a half gigabyte message, then it doesn't have a half gigabyte buffer. It has buffer space.
It does in main memory. It doesn't have recording. I mean, the thing is that the queue for messages that long doesn't store the message, right? It only stores the envelope,
Right.
which is just a few bytes.
Yeah, but if I'm sending or receiving a really long message, then that buffer is a user space. MPI has no corresponding buffer of equal size internally.
Well, it does have a buffer of the envelope, so that it can keep track.
Yes.
So, and this is the way it keeps track of the queue. So
Absolutely, yes.
That responds to this question. If you can have tons of bits, and the system just has enough buffer in the space to say, oh, there's a message from that processor with this size, and when I'm ready, I can process it.
Yeah. But
So it keeps those envelopes separate.
Yeah, those envelopes just have a little bit of information that says, I'm processor X and sending to processor Y a payload of this size of this data.
Right. So they can never like open two envelopes at the same time. Right?
No,
Yeah, exactly.
it receives processor. We'll get into that later. But processors talk back and forth. So if I'm receiving a message from one, then I'm taking the data out of the network and putting it into my user space buffer. If at the same time another message comes in, then I tell that processor, I'm not ready to receive from you. So it's not a complete push model, it's a rendezvous. So if someone wants to send to me, it says, I have this much data coming, are you ready to receive it? And I tell, no, hold off. And then later I tell it, okay, now I can receive your data. So it goes in a back and forth dialogue.
Okay.
There's no chance of overwriting.
Yeah.
But the precise mechanism is tricky. Okay. Oops. There's my mouse.
I'm going to go ahead and stop you from presenting. You can still be on the Hangout, or you can join it later. You can put your laptop with phone. And I'm going to display something that says that we'll be back at 1.
Okay.
Because it'll give 10 minutes for the
Yeah.
children.
Okay, so I've just posted that information. I can leave my laptop here.
Yeah. I'm just going to
I'll just
switch the presenter to my laptop real quick so I can just display a break message.
Okay. You mean the screen share? Very good. Yes. Huh. I have lost one projector.
the syntax on this slide, is that one for C or is this just C++?
Both.
Both, okay.
Always, for most practical purposes, C++ is a superset of C.
Oh, yeah, I was more asking for C, just because I know that there's sometimes like, when you're doing that, like before you can define cast a variable in the declare, sorry, yeah.
That's actually, I love that syntax. So you give the binary by minus and C99, C fixes.
Oh, okay. No, I was just wondering if there's also this, which is securing
So that's actually.
as a cast, okay.
Oh, yeah, that's really cool. It says, it almost says, look at these bits and now pretend that they are. So
It's like an allocation, like a memory allocation.
no, if you have a routine that absolutely needs an integer and you have a real number that you can cast it in, which does a, so it creates an integer that is a rounded value or truncated value. So it actually creates a new integer. But I wouldn't consider it memory allocation.
Okay. And how would that differ from if you were declaring?
Flip back between what and what?
Back to yourself.
Oh, goody. Apple decided that full screen means less than full screen.
Go to.
No, it's fine. Come on. Come on.
Double tap on the top.
Uh,
I'm going to double tap on the top, and we could probably minimize the screen capture on the bottom. Yeah, that works too. Now we're seeing the side. Double tap on the banner.
no, it goes away.
Okay, let's bring it back up.
Oh,
Go to preview, and you can go full screen from there or view.
Wait, which one was? Okay, this.
If you go to view right here, you probably go to presenter, full screen view.
Yeah, but I don't want that because then where's full screen?
Or slideshow.
Then this disappears. See?
Yeah, there you go. You know.
See if I can manually drag this out.
There you go.
Yeah.
That's the limitation.
Oh well. I hope this is readable enough. Software is misbehaving.
You can see
Yeah.
presentation, so if you wanted to, you could bring up your terminal to the left of that.
Yeah. Okay. Where were we?
Exercise mode.
Okay. Did everyone manage this exercise more or less? No overly big problems. Okay. So I've seen one or two of you write your broadcast statement, and because there is a root process that does something, you say, if my rank is root, then broadcast. Nah, that doesn't work. A broadcast is a collective call, meaning that everyone has to call it. So don't put it in a conditional statement. That doesn't work. Unless both branches contain it and you don't make any conflicting specifications. Okay, so I hope that everyone got that sort of working. Random numbers. Yeah, looks good. Okay, in the in broadcast and reduce, there is buffer, and then there's a count and a data type. The count, I know there are 32 processors involved, but the count is not 32. The count is 1 because you're reducing one number. Everyone has one number, so you're reducing one MPI integer or MPI whatever. Now, what happens if you reduce 2? Okay, so suppose you have a complex number and C does not have support for complex numbers, so you store it as 2 doubles, and you want to find the minimum real and the minimum complex value. So you make a buffer of size 2, and then you do a reduce. So you say send buffer, everyone has 2 numbers. Receive buffer, the root gets 2 numbers, and you say 2 MPI double. So what would MPI do then? So that was exercise 10. It says experiment with that. If everyone has 2 numbers and you do a reduction, does it then take the maximum of all the mins of all the 1s and the 2s combined? No, it does a pointwise. is minimum. So if you have an array of numbers and you find the minimum, then everyone has an array of the same length, and you do a point-wise reduction. Okay, I will not make you do this exercise. Gather.
The point-wise as opposed to.
Completely global.
Okay.
If everyone has an array, and so I have 10 elements, you have 10 elements, this one has 10 elements, and so we have 1 million elements together, and you want the overall minimum, that's not the way to do it. How would you do that? Nope. Everyone has 100 elements, you have 100 processors, you want to find the minimum of all 10,000.
Oh, you mean the correct way, yeah. You would reduce, but you would have 100 as your count, right?
So if everyone has an array and you want to have the overall maximum or minimum, then everyone would compute their local minimum, and you would do a reduction of just one number. That's the best way to do that. Okay, gather, scatter. So gather is everyone has data, and you want to bring it all together into a long array on the root. Or scatter, the root has an array of data, and everyone needs to get part of it. So in this case, you have a send buffer, which only has meaning on the root, and then and a receive buffer. And in this case, there are separate send counts and receive counts. That is kind of deceptive. The send count in scatter. So in scatter, you take a big array and you send everyone a part of it. The send count is not the total length of the array. It's the number of elements that you send to each processor. This is very confusing. The first time you program it, you will do it wrong. Likewise, if you do a gather, the receive buffer is much longer than the individual send buffers, but that does not mean that the receive count is a really big number. The receive count is how much you get from each process. Don't ask me why it's like this. That would take a lot of explaining. Anyway, I don't think, let's see, how far are we? Okay, so just to have you done this, let's do exercise 11. You have most of the elements in place. You have a program that, exercise 9, you have a program that computes random numbers. And now instead of a reduction, do in exercise 11 a gather. So this was the thought experiment, the question that I gave you initially, right? So you saw we started with showing the 4 different scenarios, the 4 different collectives, and then the question was, how do you do the following in terms of these? And now the third bullet point is everyone has a random value, and you want to print out who has the maximum. So that means that the root does a gather, and then the root goes through the array and prints out the maximum happened on this processor. Okay, please do exercise 11. Take your code for exercise 9 and make a copy. Do this exercise.
So two quick questions. One, I'm still confused. So this thing count is just how many things you're sending, you're reducing the process. But what is this data? Is that just what you can specify who is the root?
Yes.
Okay.
So if you want to do a reduction on process 15.
Okay. And then
It's kind of convention to use number 0, but in the case I actually find to use the last one.
okay. Okay.
But it's arbitrary.
And then finally, there's another
So, like now, tomorrow we get some derived basic for now, thinking sending it as a double receipt as 8 bytes. Not all of those will do that. It's conceivable. Oh, oh. No, I want to exercise. Okay. Oh, yeah. Good point.
As Cyrus pointed out to me, there is actually an MPI operator that allows you to do this with a single reduction. But this exercise is really intended to use gather. I want you to use the MPI gather call. So it's not a question, what is the best solution to this problem? It's to use gather. Yep. Cyrus, feel free to come up with an exercise that could not be so easily solved.
It's specifically for gather. No, it's so unless you choose adjustment. So in this case, there's one chance of data.
The size, gathering each process system.
All that.
It is a little more yes. That's what's proposed. So let's but as long as you have your working hour. Yeah. Most people morning people starting the sharing. Yeah, I'm gonna talk to that expert about what I might. Yeah. Talk to him a couple of times. Just for some reason. The Chrome hangout just won't recognize it. Yeah, it's nice.
Is that a USB mic or?
No, it's some type of small red HDMI converter underneath it's sort of the media side.
Well, this seems to be.
Now it's gonna create it.
I want to be. This is work.
Yeah. I was just looking at this.
If you were getting strange results, that's good. Correct.
So, in order for this to I can't fix it.
Anyway,
So, you have to allocate this.
okay, so that's the array that will contain the gamut results. That is probably necessary root for everyone else.
Okay. So just the thing to do would be declare it, say it's null, and then allocate that.
But
Yeah. I'm just curious.
Yeah. Yeah.
Sure. Do you want to
Oh, the receiver A should be. Okay, so
Okay.
Oh, right, so
Everyone is analyzing data, but the data doesn't make any sense except for the root.
right, so I want to be just on.
If you now read subroutines, then you can, so if you now have to make a sound.
Right.
If you make it dynamically, then you could, for instance, not create on everyone, but not the root. Just.
Oh, I can create it dynamically right on the page itself. Would it be after the gather or would this be before? Right. Okay.
I said.
And I guess I'll try that. That's what you think.
Leave it like this for now.
Okay.
But at least in your case, if you're not so root, you should not be doing this analysis. Because, it's the data and the array do not set
Exactly.
or it's all zero or something.
Yeah.
Use. Receive buffer, this will be the length of the send buffer times the number of processes. So if everyone has a send buffer, 2 elements, and each of 25 processes, and the receive buffer is 50. So just gather fixed processes in an array according to this would so the index of the array see things finding functions. Everybody's my ring. Okay. So now this is the section where meaningless.
Okay, I see pretty much everyone ignores the bullet point that I pointed to explicitly. In gather, the receive count is not the total length of the buffer. It's how much you expect to be coming in from each process, not all together, but each. So that means that if you do a gather, then typically it will have your send buffer and then one MPI double, and then your receive buffer, which is bigger, one MPI double, okay? So the send count and the receive count are typically going to be the same number. As someone was asking, does it make sense to have different send and receive types? Yes, it will. By tomorrow, 11 a.m. or so, you will know how that works, okay? Right now, the send and receive type will always be the same. Send count and receive count, it's counterintuitive, but they will be usually the same because the receive count is how much is coming from each process, not all together. Okay, does everyone sort of have this exercise? You trust that you can finish it? Okay, a little bit of lecturing. So you've seen broadcast or reduce and gather. We didn't do scatter, but that's just the inverse. Scan or parallel prefix operations, it's like a reduce, but with partial results. So suppose I am process of 5 and I don't want to know the maximum that everyone has. I want the maximum of 0 through 4. That's a scan. So this typically happens in indexing stuff. So suppose this process has 5 elements. This one has 17. This one has 22. This one has 4. And You pretend that all these little arrays are one big array together, and now I want to know, okay, my 0 location, what location is that in the big array? So that's the sort of indexing stuff that you would use a scan for. Scan is an extremely rare operation. I'm just mentioning it. Blah. Okay, all reduce is like doing a reduce, but not with a root. Instead, you leave the result everywhere. All gather is a gather not onto a root, but onto everyone. So the question is, how would you simulate an all reduce with routines you already know? So all reduce is reduce, but leave the results everywhere. That is equivalent to what other routines you have seen? Reduce followed by broadcast, yes. So an all reduce would be the same as reduce onto a root and then broadcast from that root. Okay, what's the point of having just one routine? Shorter code. Well, it's a general principle that you should not spell things out for the compiler or the runtime system. If a library has a big routine that does everything, then it's usually good to call that one because it can do internal optimizing. And in fact, no, this 2-day course is not long enough to start discussing the theory of collectives. But an all reduce is a reduction, which takes a certain amount of time, and then a broadcast, so it's kind of a fan in, fan out. So they probably take the same amount of time, right? Well, the interesting result is that you can actually do an all reduce in the same time as a reduce. So that's a factor of 2 time savings. So it's the conceptual point that you're actually spelling out what you intend to do. Sorry, you specify what you intend to do rather than trying to spell it out for the compiler, and it's actually more efficient. Okay, the gather scatter was bringing in information from all processes or disseminating it. Now, if it's not just individual data, but it's also individual data sizes, then you can do a gather V and a scatter V, which is a pretty complicated routine. So you have a send buffer, send count, send type, receive buffer, receive count, receive type, but there is an extra parameter, namely displacements. So if you do a gather and you're not getting the same amount of data, then the receiver also needs to know, okay, process 5 is going to put it in exactly this location, and you have to tell it where it goes. So programming this is a headache. You have to construct that displacements array. I'm just mentioning it. All-to-all is an extremely rare routine. You hardly ever need it, and in fact, the implementations that exist are not terribly good. Barrier. It's a way of synchronizing processors. So you want to make sure that all processors are at the same point in the code. So if you do a barrier call, then every process will wait there until everyone else does the barrier. Okay, this sounds really useful because you want to make sure that your code does the right thing, and this is never necessary. With the one exception of aligning processes so that you can get reliable timing, barrier is practically never necessary. Usually the way you write a code, it's not possible for your processors to get out of sync. Hey Cyrus, who was that in HPC that was doing a project with some ECSS user? One of our colleagues worked with a user code and it had 100 barriers, and you did that? Clay, okay. So he took 253 barriers out of the code. The code was still correct and it ran 5 times faster, something like that. So barriers are basically never necessary. Okay, so when I started telling about collectives, there was a question about that necessitated me saying something about the internals of collectives. So if you do a broadcast or a gather, you can do it, for instance, by having the root send a message to everyone else, or if you do a reduction, the root receiving from everyone else. Okay, now you need to know that your typical network card can only send one message at a time. So you can have a simple performance model of messages that every message takes a fixed amount of time for setting up switching circuitry and God knows what. And then that's the alpha term here, and then a amount of time per byte or word sent. So the simplest model for communicating is ignore the fact that there is a speed of light and that you have copper versus fiber and that you have a multi-state. Let's just say that between two processes, it's always the same behavior and the time is basically a one-time setup plus a time per byte or word. Okay, now the way networks are, the setup is probably 1,000 times longer than the time per byte. So if you are going to be sending a one integer message to everyone, broadcast, then if you do that as individual messages, then you get a bunch of alphas proportional to your number of processors. This is very inefficient. How would you improve on that without looking on the next slide or without remembering what I said an hour ago, 2 hours ago? The message needs to go to everyone, but you don't want to send a linear string of messages. Yeah, that is the key term. A tree or recursive doubling. So the root sends to a processor half the distance away from it, so rank is size over 2, and then those 2 send to size over 4 and size times 3/4, and then those 4 send to another 4, and those 8 send to an 8. Okay, so with P processors, how much time does this approximately take? One processor active, 2 active, 4 active, 8 active, 16, 32, 128, no, sorry, 64. So if you have 64 processors, it takes time 6 or 7. I lost count. That's a 2 log, yes. So the running time is proportional to the 2 log of the number of processors. And so in this performance model, we just ignore the time per byte because the alpha is 1,000 times larger. So if you're sending small messages, then you really want to do something that goes like this. And right, so it takes logarithmic time. Yep. That's it for collectives. So collectives are operations where everyone is involved. You need to send data to everyone, or you need to collect data from everyone. We go to the next category of MPI routines, and we'll spend the rest of the afternoon on that. Point-to-point communication. So instead of doing something overall as you do in a collective, now you identify process 2 and process 5, and they need to exchange data. So that's point to point, from one processor to precisely one other processor. Now, where does this come from? in many scientific codes, the reason you do stuff in parallel is maybe it's faster, but also you can accommodate much more data. So often you have an enormous finite element mesh or something like that that you spread out over your processors. So conceptually, there is one big array. It's just that everyone has only part of it. Okay, so if I say distributed array, then this is not something that actually exists in your programming language or in your library. It's a concept. A distributed array means everyone has an array of their own. Every process has an array, but together they pretend to be a big array. Okay, so now the problem is that the big array goes from 0 to 10 billion, and you have 1,000 processors, so everyone gets 10 million elements. So everyone gets 10 million elements. Everyone does a malloc of 10 million, but that means that everyone has an array that goes from 0 to 10 million. How do you get to the 10 billion? Okay, that's because you have to do a translation. So in your C programming language, your SPMD model, everyone only has the local numbering. But in your mind, there is a global numbering. And the global numbering is what the algorithm is based on. So you find yourself writing the following quite often. You compute your own, you compute my first array element. Where does that one fit in the big distributed array? And then you write a code where you say, okay, for all of my local elements, I put something in the array that is a function of the global numbering. So you translate your local numbering. Your local number is the global number of your first plus the local number. You find out where in the big distributed array the start of your array fits, and then you loop over your local array, and you say, okay, a location in my local array is this location in the global array, and then I set something in my local array in global coordinates. Now, okay, so this is the way that you connect local data to the overall working of the program. Okay, exercise 13, just to have you write something like this. Make an array. Okay, we want to compute the sum of squares. Actually, hint. Use real numbers to compute this, not integers. You want to compute sums of squares, and we do this by everyone constructing an array and then summing up the elements, and then you need to globally sum it together. And yes, you can do this without an array, but I really want you to create an array. So this is kind of a simplified model for big vectors in finite element calculations or something like that. Okay, exercise 13.
thing times itself.
Yeah.
The power function probably takes the logarithm than power, for example, and multiplication of 2
I see that the exercise leaves one detail somewhat unsaid, and I think I heard Cyrus explaining it to someone. In the third bullet point, it says use a collective operation to compute the sum of the array values. So you have to be slightly careful there. So if everyone has their own local array, if you would do a reduction on those arrays, then you only get pointwise reductions, and then maybe the root would still have to go through it. If you do it that way, then there is a lot of data going through the network. It can work that way, but it doesn't work that way if everyone has a different amount of data. So the best strategy is everyone has a local array, and then everyone makes the partial sum of just the local values, and then you do a reduction of all those partial sums to get the global sum. So that's how I wanted you to implement this. And I'm sort of writing that code out here. So you start with a segment where you compute what is my first and my last index. I'm actually allowing for the case where it doesn't perfectly fit. Then you create an array. My values is a malloc of number of local elements. I guess I could do it statically. You go through a loop where you go through the locations in your local array, which is 0 to something. And you set the values. You do a loop that goes through the local array. And then you do a reduction.
for both the flag using C99. So I would put that with
Somebody's making a comment online that I should see my last one, is my first plus one, which sounds about right. I'm just trying to figure out if it's easier than most for some reason.
what editors.
VI can do those. Anyway, we'll show you source.
I snagged some of this from you just because I was stuck with the tedious exercise for a while. I ended up having to.
That's the essential part of it.
Yeah, yeah.
So my first was never going to start at zero.
It really doesn't matter. All I know is just he's using the across the number of elements.
Yeah, but then as long as
If
he
he covers both the first and the last group, that should be plus one. So 3 minus 1 is 2. I think we'll get covered one or two. Okay, cover 3.
well, it depends on how you do
Yeah.
it.
Yeah, that's the best one. Label can equal 0 and then goes through and look.
That's fine. Because I mean, that, it's the number of.
So it has to be smaller or equal than that. I think it's missing one.
I think it probably is too. But it's only gonna actually that one last. maybe it's single position, maybe it's You're checking this with Alpha. Okay, why not? I think the idea of doing computation in natural language is fundamentally misguided. When it first came out, I asked it the speed of sound in water told me this. What did I 1 meter per second in furlongs per fortnight gave me an answer. The speed of sound in water in furlongs per fortnight, and the two ins, of course, confused it. Natural language is just a 1 meter for this stuff. Quite surprisingly.
To begin with. Because.
My brother is an aerospace engineer. He said he was starting with all of his homework furlongs per fortnight.
You look like it.
That's when the professor starts saying SI units for everything.
Anyway, go from alpha. If you type natural language in Google, it usually comes up with the right answer anyway, even though it doesn't understand language.
Okay, I looked at a couple people's screens, and I think everyone is getting the basic idea. Let's see. Yeah, I think everyone is getting it. So the point of this exercise was the translation between local and global numbering. Oh yes, and why are integers? Did everyone do this in real numbers? Why are integers a bad idea? Yeah, computing squares and then cube roots, you're pretty much overflowing your integer range. What's the largest integer that you can normally represent? 2.14 billion. What is 2.14 billion? That's 2 to the 31. You have 32 bits for an integer. 1 bit goes to the sign bit, so you have 2 to the 31. How much is 2 to the 31? Well, I just said that, but why is it? Okay, 2 to the 10 is 10 to the 3, right? No, but close enough. 2 to the 10 is 10 to the 3, so 2 to the 30 is 10 to the 3, 10 to the 3, 10 to the 3 is 10 to the 9. There's 1 2 left, so it's 2 billion. Turns out to be 2.14. Okay, so don't use integers, they overflow. Use floating point numbers. Okay, so initially I tried to do it for irregular data sizes. So in this exercise, I said assume that the global parameter is a multiple of the number of processors, so everyone has the same number of elements. That's to make coding a bit easier. Suppose everyone has different amounts of data, then every process has different amounts of work, and so they're all computing their local sum, and then they're going to be doing that reduction, and that reduction is when they all have to work together. So if someone takes way more time on their local sum than the others, then that process is probably going to hold up the rest. So having different amounts of work per process is a bad idea. This is known as load balancing or load imbalance. And so So suppose you have an n global and you have the local that is, and you just do integer division. And if you do it this way, it's with truncation. And you compute n global modulo to find the number of elements that are left at the end. And so you say, okay, the last processor, I just give all the extra elements. Okay, this is precisely the wrong way to do it, right? Every process has the same amount of work, except one has more. So you're pretty much guaranteed that everyone is waiting for this last process because it has more work. It's much better to give everyone the same amount of work, except for one who gets a bit less. Or maybe you should take the excess and spread it out over processors. So this is not the right way to code it, and there are better solutions, which I won't go into. But keeping your amount of work approximately the same on every processor is a good idea. Unfortunately, you can have a code where the work dynamically increases or decreases, and then it becomes unbalanced, and you have to maybe move data between processors, and that is all very tricky, so we're not going into it. But be aware of the potential problem of load imbalance. Okay, so why was I making you do this stuff with an array? Well, that sort of thing happens in practice quite a bit. If you do inner product calculations, then you have a vector and it's spread out over all your processors, and you have a vector x and y, and let's say they're both divided the same way over all the processors. So how could you compute the inner product? Well, you could say, okay, processor 0 is going to gather both of the vectors in their entirety and then compute the inner product. Okay, that's a really bad way to do it, because then processor 0 has much more work than everyone else. So the right way to do it is everyone computes their own part of the inner product, and then you combine the parts together. So so you have this code where you gather the local inner product, and then you do a reduction into the global inner product value. And this is the right way to do it. If the array is reasonably divided, then everyone has approximately the same amount of work. And you note that in this code, there is no translation between the local and the global numbering necessary. All of this illustrates what we started out with, is the notion of a distributed array, right? So your local arrays are conceptually part of a big array. I'll let you do this some other time. So now let's do a serious calculation, not something trivial like just summing up an array. So for the people here in the room that know what finite elements, finite differences, finite volumes are, this is a toy code that does something that stands for finite differencing, whatever. So you have two arrays. You have a distributed array X and a distributed array Y, and every element in Y should become a average or whatever of a couple of locations in X. And we don't worry about the boundary points. You can assume that they're 0 or whatever, they're constant. X and Y are both distributed arrays, and the tricky part is at the boundaries of the local parts. So in the middle of a local part, it's easy. Yi is just xi, I minus 1, I plus 1. But at the boundary, for instance, let's look at the, okay, I cannot highlight in a picture. But let's look at the element that is labeled I sub 1. It's the first element of the second processor. So it comes from X on the same processor, xi plus 1 on the same processor, and xi minus 1, which is on another processor. Okay, so this sort of calculations is why you have point-to-point communication. Processor 1, the second processor, needs to communicate with exactly one processor at its left boundary, and the same story at its right end. It needs to get one element from a processor on the right. Okay, so we first did collectives where all the processors are communicating with each other. This is much more limited. One processor is communicating with just two others. If your array is 100 billion long and you have 1 million processors, still every processor only communicates with two other processors. So it's a very small number of communications. So that is characteristic of point-to-point operations. Okay, so how do you do point-to-point? In MPI, the basic mechanism is, the term is not mentioned, it's called two-sided communication. It doesn't say so, nope. It's called two-sided communication. You cannot just drag data off another processor, or you cannot put data on another processor. It has to be a matched send and receive call. So in this picture, the second processor does a receive of data that comes from the first processor. So the first processor is sending its last element, and the second processor receives it to use in its first calculation. So it's a matched send and receive. One process sends to one specific other, and the other does a receive from one specific source. Okay, the simplest code that you can do with send and receive is a so-called ping pong. A sends to B, and B sends to A. Oh, goody. Okay, so there are two instructions in your MPI language. There's send and receive. Okay, we do a ping pong. I'm A, you B. Okay, so I'm A. I do send. What do you do? Okay, and now you do. And I do receive. Okay, so I am process A. I executed the code send receive. He is processor B. He executed the code what? Receive send. Okay. So that's how a ping pong works. So I need to do send receive. He needs to do receive send. But we have SPMD. It's the same program. Okay. So how do you solve that? How do you solve that problem that I'm doing something different from you? If statement. If rank is process A, then send receive. If rank is process B, then receive send. You're trying to think in global terms. You need to think of what is the code you're writing that if two people execute the same code, what makes them have different behavior? If statement. Don't think in global terms of data goes from here to there. I am one process. The only thing I can do is send. And there is no from here to there. There's only send or there is receive. Okay, so this is what it looks like. If I am process A, then I do a send and a receive. If I am process B, then I do a receive and a send. Okay. The send and receive routines in MPI look like this. Buffer count data type, the way you've seen it half a dozen times before. If you're doing a send, then the next parameter is destination. So you have to say where you're sending. You can specify a tag. If I am sending two items to the same processor, I can label them as this is tag 1, this is tag 2, and so you can distinguish what purpose or so. Tags are very rarely necessary, so I usually just put a tag of 0 on it. And again, the MPI communicator. Same in C and Fortran. All right, this is where Python people need to pay attention, because there is send with lowercase s, which is the native one, which is beautiful and slow. And then there's the NumPy one with a capital letter, which, yeah, I need to describe that a bit more clearly. So the self, it's a prototype. Don't type this code directly. So the send with a capital letter can only send NumPy data, and it's very efficient, but it's not as general. Likewise, receive. Okay, the send is buffer count data type, destination tag, communicator. Receive is buffer count data type, source tag, communicator, and then there is a final argument, namely the status. So what is the status? In MPI, you can do things like saying, I'm not receiving from a specific processor, but I can receive from anyone. And then the status object allows you to say, okay, where did this message come from? As I say here, just specify MPI status ignore. That is good enough for all the exercises you're going to be doing. But there are a number of cases where you don't know in advance precisely what is coming in or where it's coming from. And so then you need to do the status. Okay, so buffer count data type, destination tag, communicator, buffer count data type, source tag, communicator, and a status which you can ignore. Okay, there's the two syntaxes. Okay, Python people. So the native syntax says receive buffer is com receive, and do not do the self. The NumPy one says com receive, and then this is the receive buffer. So why is there two buffers in the native call? You can ignore this one. Anyway, the two different modes have a slightly different syntax. So the NumPy one, the buffer is a parameter. The native one, the buffer comes out. Okay, write a ping pong. It's the next exercise. Okay, so to write a ping pong, you need to have a process A and a process B. So you could, for instance, send from rank 0 to rank 1. Now, for the people that have been in the machine room, you saw the node, and it has two chips. So node 0 and 1 are probably on the same chip, so that should communicate very efficiently. They just need to copy data over a fraction of a millimeter. There are 8 cores per chip, so probably the first 8 ranks go there. So if you communicate between 0 and 8, you're probably communicating between the two chips, but still it goes very efficiently. But so remember the exercise where you did MPI get processor name? That showed you that half your processes are on one node, half are on another node, and the only way they can communicate is through the network. Okay, so try your ping pong program with 2 ranks that are on the same node, and try it with 2 ranks that are on different nodes, and observe that the timing is rather different between the two. Use MPI W time. That's the wall clock timer. Let's see. Yeah, start doing that. Don't do just one ping pong. Do 100 in a row, and then calculate the average or something. Okay, edit. Wanted. Right. Somewhat deliberately, there are no exercise sources. Yes. Yeah, all the exercises build so much on each other. Tags are very rare. The sender and receiver have to agree on the tag. Use 0.
Because part of it is the card might be sleeping.
Yeah, but if you know, is this something established that makes the information with the same mode? So
Yeah.
yes, yes.
Okay, I'm gonna see. I'm gonna see how long, like.
Yeah, so call the timer twice in a row and see what the timer is. That tells you what the timer is. Make a copy of your file.
Just wanted to do the all time. And I'm just bringing it out.
You understand my question though, because like.
one was the same thing. I did that in hindsight.
Yes, okay. As long as you recognize this data.
I realized that in hindsight.
So you have a send buffer and a receive buffer. So rank 0 is sent once you receive it. So 0 has something in the send buffer. And then 1 gets something in the receive buffer.
So say power run 0, I send a verify, but I need to make sure that I receive the
You send it. So every process makes a send and receive buffer. Two is a send buffer. Everyone has a send buffer and a receive buffer. And then process 0 set the send buffer. 1 will receive the receive buffer. And there's no relation between them. Every process has two buffers. There's nothing corresponding.
So the only thing that send and receive is the destination.
Yes, for 0 sends to destination 1, and 1 receives from source 0.
Okay.
Oh, I. I'm doing two. I'm doing two that are far away from each other, and I increase the data size to 100. These two are also from a single. So there's not much difference between one element and 100. These two are also the same amount. That one is. This one is the outlier, if anything. This one, all just one single element. 100 times. Stepping back to point timing there. Goes much faster. Like a two neighboring guys. I would try to make these speedy. Only 5 microseconds.
It's 10 to the minus 6. Lose a factor of 3.
Switch this to other average.
Let's, so for latency test, that would be this guy has you should put in some.
Okay, is everyone getting this? Are you getting a number that is between 10 to the minus 4 and 10 to the minus 6? 10 to the minus 6 is optimal. You have to loop at least about 100 times would be enough, but make it 1,000 or 10,000 times, and then compute the average time. So you put A single timing doesn't mean a whole lot. So there could be a lot of variability. And first time you send something, maybe the network card needs to be initialized. So you start your timer, you do 10,000 ping pongs, and then you compute the average time. And then you should get 10 to the minus 5 or so. Okay, everyone has this working?
I can only ping, it's hanging. Oh, yeah, I send.
Because you had one sent to itself.
Anyone else need some help?
Okay, ping pong. So communicating between two processes. Okay, we have to go into some of the intricacies of how communication happens in MPI. MPI send and receive are so-called blocking operations. So it would be so nice, left picture, if a process could do a send and then the data disappears into the network, and when the other side does a receive, the data comes out of the network and goes into its buffer. This doesn't actually happen. The network has no capacity as such. So if I do a send to you, but you've gone to the bathroom, then there is no receive happening for a while, and so my send is blocked. So my process, I try to do a send, and if the other process is not receiving, then my code is stopped. This doesn't happen in sequential code. In sequential code, you're always doing the next instruction. In this case, the next instruction cannot be done until the send is complete. And completion of the send depends on the other party doing the receive. So that's called a blocking operation. So if the receive happens later than the send, then the sending process is blocked. If the receive happens earlier, then the receiver is waiting for data to come, but the sender is not doing anything yet, and so the receiver is blocked. So if your code is not nicely synchronized, you can actually lose performance. There are more serious problems than just performance. You can have the following. So suppose you have process 0 and 1, and they both say, okay, I am me, and there's the other, and now I'm going to receive something from the other, and then I'm going to send data. Well, if two processes both start waiting until the other one receives, and then they send, you have a complete case of deadlock. Nothing happens. They're both waiting to receive, but no one is doing a send. So you have a code that is that it compiles and it passes every semantic test, except that the resulting execution deadlocks. Okay, so that is a problem that you can have with parallel codes. You get deadlock. Now, if you write it this way, first receive, then send, you can pretty much guarantee deadlock. If you do it the other way around, and both processes are trying to send and then receive, it should also deadlock, because you cannot push data until the other guy actually receives it. However, your typical network card has a little bit of buffer space, and so depending on various parameters, a message of 100 bytes may actually go through even if no one is receiving. So this sequence, both of them are sending and then both of them receiving, may actually work. Still, you shouldn't write code this way. One of my favorite consulting tickets. So me, Carlos, Cyrus, and Antonio, who was here earlier, are in the HPC group, and we take turns with 10 other people helping user tickets. And my favorite ticket was a user, and he ran his code when we had an IBM Power 2, and the code ran, and we decommissioned the Power 2. He ran the same code on the Power 4, and it didn't work. And that was precisely because he wrote this. And so he was counting on small messages going through, even though the code is not correct. And from one version of the IBM to the next, this limit had dropped, and his code was suddenly hanging. So you cannot count on this sort of stuff. But it's a subtle point. Okay. So as I mentioned, all right, yeah. So sending and receiving is not a one-sided operation. There is back and forth talking going on. So the sender says, "I have this much data for you." The receiver says, "Okay, I'm ready. I have a buffer." And then the sender says, "Okay, here's the data." And then it goes through the network, and the receiver says, "Got it." And then so the sender does a send operation, and under the hood, it talks back and forth a couple times. And so whatever instruction comes after the sender waits for this whole back talk to complete. And so only when the receiver says, "Okay, I've received everything successfully," that's when the sender can execute the next instruction. So an MPI code, whatever comes after if the sending instruction finishes, it means that the whole transfer has successfully been done. That's the definition of blocking. So you're stuck in your send instruction until the complete send has actually been received. Okay, people are sitting too far apart here. Okay. The three of you stand up and take an object, mouse, pen, whatever. Come here. I love theatricals. So what is the program? We are going to try to give a piece of paper to your right neighbor. Okay, so let's face the rest of the class. So I am your right neighbor. Everyone is holding an object. Put your left hand in your pocket. You only have one hand. Okay. So everyone is going to give something to the right neighbor, and then so giving to your right neighbor means giving it and then getting something from your left neighbor. So the program is turn to your right, give, turn to your left, take. Okay, I don't have a, everyone, turn to your right. I try to give something. Doesn't work, right? We're stuck. Okay, but I don't have a right neighbor, so I can now turn. I can get this. Thank you. So your giving part is done, so now you can turn, you can take from him. Now your program, first instruction succeeds, and so you can, okay? Thank you very much. Okay, the point here is that giving data to your right neighbor should be a completely parallel operation. If you could do it one-sided, just put it on their desk or put it in their pockets, that it was completely parallel. However, because MPI works two-sided and it has blocking operations, it means that what should have been a parallel operation got sequential. First I receive, and then he can receive, and he can receive, and then he can receive. So here you have a very tricky situation. You have a program that is syntactically correct, semantically correct. If you run it, it computes the right result. It is just way too slow. So it's not deadlocking, but it should have been parallel. It should have been a 1 second operation, and instead it took proportional to the number of processors. Okay, so sending and receiving with blocking and two-sided is very tricky, and there are several issues. There is this deadlocking, and then there is this unexpected serial behavior. We have a utility called Tau, Trace Analysis Utilities, comes out of Oregon. It's very nice. It's fairly easy to integrate it with your code. And so I wrote this program in MPI, and I made a trace of it. And you see that this is the last process, or maybe it's the first. So it receives, and then the next one receives. So kind of hard to see, but you see the white diagonal lines. So everyone starts their send at about the same time, but it cannot complete. The last one does a send, and then the one before that can only succeed when this one has done its send, and now it can receive, and then so you get this serialized behavior. If your program does something weird, consider using Tau or Intel vTune to make a visualization of the program behavior. It's very hard to look at a program and then imagine that the same code will run on a bunch of processors and try to imagine what the interplay between them is. Okay, so the problem here is the right output, just way too slow. Okay, blocking sends and receives can be trouble. But this operation, giving to your right neighbor, should have been parallel. So how could you solve that? So with the 4 people that were just in front of the class, or in general, how would you solve this? How could you make this much more parallel? Yep, you divide them in 2 groups, and so the even people give to the right while the odd ones do a receive, and then the odd ones do a receive while the even ones, sorry, do a send while the even ones, yep. So there is a way of getting around this. It is just very tedious. Okay, we'll get into solutions for that later. Just be aware that sending and receiving can have unexpected complications. So we started saying that we need point-to-point because of operations like this, like the 3-point combination. So every point needs information from a point to the left and the right, and because of the way you divided it over the processors, every processor needs data from the left and the right. So how would you program this? So you could say every processor gives data to the right and receives from the left, but we were just acting this out. That's not going to work, right? So spelling this out completely with sends and receives is not going to work, or will give the wrong performance. Instead, there is a routine called MPI send receive, and it's a great routine for doing pairwise exchange. So if you can somehow arrange your computation as everyone does exactly 1 send and 1 receive, then you can combine them together, and this will work without deadlock. So because in this picture, processor 2 needs to receive on its left side and processor 0 needs to receive from the right, you can pair them off and you do a send receive call that implements this. Okay, so what does this look like? Well, so you need to pair off the processors, and so of course there is a problem with the very first and the very last, and so your code typically looks like this. If you are not the first one, then you have a predecessor which is your rank -1. Else you put the predecessor to a predefined value, MPI proc null, which means no processor. And if I am not the last one, then I have a successor, which is my number +1, otherwise it's null. And then you do a send receive where you say, I'm receiving from my predecessor and I'm sending to my successor. So that would be a way. This picture does not quite. So that is this. I am receiving from my predecessor and I'm sending to my successor. That is not the correct picture. So, this way the send receive call solves the deadlock problem. The implementation is such that you cannot get the, not deadlock, but the serialization behavior. So if you have computations where you can nicely pair everything up into one sender, one receiver, then this is the way to do it. Okay. Ignoring tau, do exercise 17. So every process has one item of data and it needs to give it to the right neighbor. Do this with MPI send receive. Hit it. MPI send receive has a syntax, so it's send buffer, send count data type, destination, tag, receive buffer, receive count data type, source, tag. So it's basically the syntax of a send routine and a receive routine thrown together. With that, do exercise 17. And we're supposed to run it at 4 o'clock. Yeah, I still want to stop after the next exercise. Yeah. I'll assign them the next thing.
This is very small, but. Yeah. Here's an actual compute that object is right here. And then 8 through 16, so it's on the second for the compute. And yeah, it makes trying to get the timings down very frustrating. But, yep, you always want it on the second. Even though for Stampede, if you go to Hikari, actually what it does is it puts the first CPUs here, second set here, third set here, fourth set here. Please
Why?
Nobody knows. Please standardize. Yeah. So this is about sending data to the right. So you send it to the right, you're receiving from the left. You need two labels.
Okay, so I did a little reducement just to kind of like see that it was doing these set receipts, basically. Initial value, receipt buffer. And then so you write, I've seen the buffer it has around this process. And so when I do that, though, getting some of the 60. Oh, sorry.
Interesting, because you're doing.
Yeah, 32. It seems like it should be 64. When I did it previously, just I had the send buffer 0 and the receive buffer 0. So they were both 0. Kind of tough to tell if I was actually sending something. So it was just something because the receive buffer was 0 to begin with. So easy to get 32. But this one, it seems like I'm leaving one out. Yeah, this seems to be some just like misstep in thinking right now.
Oh, make a loop. Sure.
But it's not.
You can do it modulo.
That's the receive buffer.
Yeah.
Do you have to use a different buffer? I mean, you have to use, like here I have two different types of buffer and receive.
That's fine. In this case, you're going to plus try, if you're doing the send receive, you want whatever content you're going to receive. What do you set?
So the send buffer is right here. This is your buffer.
I'm still using this.
Because I wanted to have a flag, like to me, to see that it had received, everybody had received their buffer. And so the only way I could tell that is if everybody received their buffer, their RBUF should have been switched to 1 because they had a buffer that had given
Right,
them.
so then this is going to make everybody.
2. And so when you look at it, though, it's 63. So it seems like somebody isn't quite doing that, which is weird.
The trick of it would be who are you sending and receiving? How many guys so how is process 0 process 2 different ways? So because how are you doing your senders? If I'm process 0,
Oh, I'm saying So,
That's where you're losing. So if you want to wrap it around, you can have a special case.
sure, that's what makes sense, okay.
Yep.
I knew I was missing just one other piece.
Oh, but you got it. Nice.
Great, thank you.
So here, this come here, my recommendation, for arrays. So this is just one data type. Everyone has just one number and you want to give that to your so you take
Everyone has.
Okay, the announcement for this course said that we would run until 4 p.m. So I'll stick around for the next 10-15 minutes to help people with this exercise. If you can do this exercise, and here's your midterm, exchange, sort, or swap sort was a name for it. Odd even transposition sort. Okay, so this is basically a parallel version of bubble sort. So to show that you can use MPI send receive to actually do something quasi useful, your midterm is implement a exchange sort algorithm. So you can do that at home tonight. And tomorrow I will continue with non-blocking communication, and then we get the next couple of chapters, which are about communicators, derived data types, just a little bit of one-sided communication. Anyway, so I'll stick around for the next 10 minutes or 10, 15 minutes or so to help you with exercise 17. You can get to do you can do 18 at home, and tomorrow we start with the next section. Okay, so that's it for today. Yeah, I'm keeping the log of the terminal session. And I've been going over some of the exercises. So yeah. Sorry, I was teaching this.
I remember quarter to 9.
Jason.
Did you close the browser?
We're again here tomorrow, same room, right? So the laptop will stay here.
Yeah, that's fine. Did you close your Hangout? I'm having try to do Alt or your command, your typical Windows or your Mac controls. I didn't want to see the other Chrome window.
Hangout is
Yeah.
in the browser window.
Yeah, it should be on Chrome.
Yeah, so it's one of the minimized windows.
Oh, there it is. All right, go ahead and just hit a X. Hit that right there. There you go.